Hello everyone. Today we will discuss a very sensitive topic, asymptotic notation. Let's say I have been given a problem. So what we are supposed to do? First, we should come up with the flow chart. Why I said flow chart? Flow chart something where we will think about the problem and will come up with a pictorial representation. If we will do this, what will happen? If we will not do this, what will happen? Then we used to make an algorithm. Algorithm is step-by-step representation of solving a problem. For solving a problem, there can be many algorithms, because there will be many solutions to solve a single problem. For example, if we have any question, what we used to do? First, we used to come up with brute force. Then we used to have an efficient solution so as to have efficient time complexity as well as space complexity. In terms of time and space, we are coming up with efficient solution. So for this, we will come up with different terminology. So for representing asymptotic notation, we have three terms. First is big O, second omega, and the third is theta. Theta is represented with this symbol, omega is represented with omega symbol, and O is capital O. So after solving a problem, we are looking in terms of big O, omega and theta. Big O is for worst case, which means in any of the case, time will not exceed, so it is the worst case or upper bound. Omega is solved in terms of best case. Best case is something that in any case we will not achieve better than this. And theta is average case. So generally we are interested in big O, which means never go beyond it. Omega is we will not achieve better than this. That is never go up to. Then comes theta. For theta, it is the average case. That means for some inputs, they will take same time. Same time when best case is equal to worst case. That means we are writing an algorithm where best case is also order of n as well as worst case is also order of n. In such case, we use theta. So theta is always used when best case is equal to worst case. But in practice, we are generally using big O, right? Now let us know these three of the cases in detail. So the first one is big O, which is written in terms of O. Now in this case, when I have been given input as n, the size of input is n, and in algorithm, if input size is increasing, so time is also increasing with increase in input. So here I can write f of n, the function of n. And what if I bound fn into CGN. That means here I will draw a line where it has CGN, and the CGN is upper bounding the Fn such that Fn is less than equal to CGN, as CGN is upper bounding the Fn, and this condition will only satisfy when this N0 N is greater than N0. So N should be greater than N0, where C and N are real numbers. So C should be greater than 0, the constant, and N0 should be greater than equal to 1. Then only Fn will be equal to order of Gn, big O, and that is only when Fn is less than equal to Cg of n. Let's understand this with an example where Fn is equal to 5n plus 4 and Gn is also a function which is equal to n. Now we have to prove Fn is equal to order of Gn, and that can only be equal if Fn is smaller than equal to Cg of n. So here I need to find C and N0 to prove this. So what I'll do, I'll write this here where Fn should be less than equal to G of n, so as to upper bound the Fn. For C should be greater than 0 and N0 should be greater than equal to 1. So Fn is 5n plus 4. So I'll write 5n plus 4, and Gn is n with C constant. Now for making this equal, I need to define this C. Let's take C is equal to 6. So here if I write 5n plus 4 smaller than equal to 6n. So if I take this here, n greater than equal to 4. I can write it like this. So if I put this C is equal to 6 such that we can prove Fn is equal to order of Gn, where Gn can be n square, n to the power n, 2 to the power n, but we need to go for the least time, as we are looking for least time complexity. That's why we always say order for efficient time complexity. So big O is such that when Gn is upper bounding the Fn. Now let's look the second term, big omega, which is represented by omega sign, and here the size of input as n, and we will calculate the time. Let's take Fn, same, the function of n, and now Gn is lower bounding the Fn function. So here I am writing Gn with C. C is constant such that Fn should be greater than equal to Cg of n, as Gn the function is lower bounding the Fn. That's why we have this sign where n should be greater than n0 and the constant C should be greater than 0 and n0 should be greater than equal to 1. Input should be at least 1. That's why we are taking n naught should be greater than equal to 1. Let's understand this by the same fn is equal to 5n plus 4 and gn as n. Now, so as to make gn the lower bound for fn, we can write fn is equal to omega of gn, right? So we can say fn should be greater than equal to cg of n, where fn is 5n plus 4 and gn is n. We will take the constant c. Here if I put c is equal to 4, let's put it 5n plus 4 greater than equal to 4 of n. So I took c is equal to 4 such that it can satisfy the condition where fn is greater than equal to cgn. And I can write 5n plus 4 should be equal to omega of n. So here this gn is lower bounding the fn. That's why we are terming it as omega. So omega is lower bound, whereas big O is upper bound. Right? Now let's understand the third term, which is big theta, which is represented with theta symbol. And if I draw this for size of input n, with increase of n, the size of input, the time is also growing. And here we will take the upper bound as well as lower bound, and these are differentiated in terms of C2 and C1. Both are upper and lower bound for f of n, where we will have n naught, so that we can write fn is equal to theta of g of n. As in big theta, we have this fn upper bounded by C2gn and lower bounded by C1gn. So we can write it C1gn smaller than equal to f of n smaller than equal to C2 of gn. For C1 and C2, the constant should be greater than 0. N greater than equal to n naught, where this n naught should be greater than equal to 1, because input will have at least the value 1. Let's understand this in terms of fn, which is 5n plus 4, and gn is equal to n, the same inputs. Now, first of all, we will take in terms of C2, as C2 is upper bounding the fn. So, it should be greater than equal to f of n, correct? So, for fn, I will take the value 5n plus 4 and gn is n. Now for proving this upper bound, what I'll do, I'll take the value C2 is equal to C. Let's assume it such that this is upper bound, and it is valid only when n naught is greater than equal to 1. Now let's see in terms of lower bound, where fn should be greater than equal to the lower bound C1 gn. So I'll write fn greater than equal to C1 gn, where fn is 5n plus 4 and gn is n. Now we have to take the C1 value such that, let's take it 1. And also n0 should be greater than equal to 1. So as Fn is greater than equal to C1Gn, we will have the value 5n plus 4 greater than equal to n. C1 is 1, so I will write as n. So I can say Fn is upper bounded by C2Gn and lower bounded by C1Gn. That's why this big theta is always termed as average case, where we always take the value in terms of both upper bound and lower bound, that is big O and big omega. Now sometimes theta is also known as asymptotically equal, that is if we have the value 4n square plus n, then we will always take the value of leading term, which is n square. That you must have seen when we solve the problem in algorithm. If we come across the n square, we will always take the leading term, not this n. So here we have seen how big O, omega and theta are contributing towards asymptotically notation. So this is it. See you in the next video. Till then, take care. Bye-bye. Thank you.